We're now going to take a look at one of the major items in mathematics, and that is the concept of function. So here we're introducing, and we'll go over the words relation, domain, and range, identify what a function is, use the vertical line test for function, find the domain and range of a function, and then use function notation. So, as we move on, let's do some definitions. Now, here are the main four words we're going to be dealing with in this section: a relation, the domain, the range, and the definition of a function. Now, a relation indicates that somehow things are connected to each other. So I think it's pretty obvious that when you see an ordered pair that we talked about in the previous lesson, that these are connected. If you have an x value and a y value, you put it on a graph, it's a particular point. So a good example of what a relation is the ordered pair. Now, the first member of the ordered pair, that is the x, is considered the domain values. And the range are the y elements in an ordered pair. So domain refers to the x, range refers to the y. Now, a function in mathematics is defined that the x element in a relation is only used once. So if we find that x element is only used once, and there's an infinite number of elements there, x is an infinite number of numbers, but in a series of relations, the x element's only used once, that specific element, then it is a function. Now, we're going to build up here to show you how, when we had that special equation, y equals mx plus b, where x, by putting a value for x, it will determine what eventually y becomes. So we say we input the x into some sort of operation here, and out comes the y. So we'll build on that as we go through. So we see, again, tying it into our previous lesson, these are all ordered pairs. They have a x value, a y value for each one. And as we look at these, the -3, a 1, a 2, and a 3, the x element's only used once. So this would be a function. Now the same applies when we put it in that slope-intercept formula. When we put a value in for x and then solve it, we come out with a value for y. And this gives us a line, and there's an infinite number of points along that line. And are the x elements ever used more than once? Well, in this diagram, they are not. So this would be an example of a function. And as we see over here, where we're talking about, let's say, A, C, E as elements in this first set, we can think of this as the x values, that what comes out of it is a y value. Now, you might say, are the x elements used more than once? Well, A, with one line from it, it's used once. C, one line, used once. E, one line, used once. Now notice the 2 doesn't seem to be used at all, while in the y value, the 3 is used more than once. But that's not part of the definition of function. The definition of function is that the x element is only used once. So this represents a function. So here are the more formal definitions. We gave a nice brief one. So a relation would be a set of ordered pairs. The domain is the first element. Now, if we're calling the elements x and y, then the domain is the x element. If we're calling the ordered pair A, comma B, which is also sometimes used for x and y, then the A is the first element. So this, whatever's in that first element position, that is the domain. And in the second element position, that is the range. So again, looking at correspondence or relation, first element, 1, 2, 3, they're only used once. So this would represent a function. All right, let's look at some others here. In example 1, it says determine the domain and the range of each relation. Well, as we look at the series of ordered pairs, I would suggest you put it this way in your notebook: domain equals, and then we're going to set it up in roster notation. So we have a 2. Now we see the 2 is repeated, so this would not be a function. And when the x element, the domain element, is repeated, in our roster notation we only write it once. So then a 0 and then a 3. But we now know that since the x element is repeated, this series of relations is not a function. Now for the range, we have a 3, a 4, a -1 is repeated. We only write it once. Now in example B, we're picking up on our x elements. So it would be a -4, -3, -2, -1, 0, 1, 2, 3. So we would just string that out. That would be our domain. Now for the range, the only element in the range that's used is 1. And since it's repeated, you only write it once. Now for letter C, we would write for our domain what is in the blue, because these are the first elements. And by the way, this in letter B would be a function because the x elements are only used once. Now as we look at this, is this a function? Well, looking, the cities are only used once. So this would be a function, and we would list that. Now, since 195 in the range here is not used, or 35 is not used, we wouldn't list that in the range. And they are listed in your textbook. Here we're looking at function. And again, a function is a relation in which each first component, that would be the x value, in the ordered pair corresponds to exactly one second component. Again, the shorthand way is the x element is only used once. So, in example 2, we're asked to determine whether what we have here as data is a function. Well, let's look at this one here. So -2, 2, -3, 9. The x element is only used once, so A is a function. Well, how about this graph here? Well, we have a -3. Now note 0 is used once here, and 0 is used once there. So 0 is used twice as an x element. So this is not a function. All right, letter C. People in a certain city. That's your input. Each person's age. The output is a set of non-negative integers. Now, is a particular person used more than once? No, each person is unique. So this element is only used once. So this would be a function. And we'll do this one too. So we have a 3, a -3, an 8, and a 9. The x element, the first element, is only used once in each relation. So this is a function. Now here, this is a -2 for the x value. This is a -2 for the x value. So this is not a function. Now, as we saw in the previous example, when the x element is used more than once, those were ordered pairs. So those would be a relation. Anytime you connect numbers, like in an ordered pair, that's a relation. But is every relation a function? That's the key. All right, so let's take a look at example 3 here. And we're being asked, in this equation, and remember this form, just to review, y equals mx plus b. That's what we see here. Is this relation a function? Well, notice when you would make a t-chart, you would only put your x value once. You wouldn't say another one because it would be the same. So in looking at this, generally speaking, whenever you see something in this form, this is a function. And we'll see that built on in future lessons as well. And this one also in slope-intercept. This is a function. In example 4, they're asking, is this relation also a function? Well, notice now this is not linear. And in fact, if we made a graph of this equation, it would look like this. Now, you might say, these are your x values. Now, this is a 1 here. Well, up here, this would be a 1, comma 1, let's say. And over here, this would be a 1, comma -1. So are the 1s used more than once? And the answer is yes. So this is not a function. Now a sister of this would be y equals x squared. And we did this graph. And remember, this one looked like that, going right here at 0 as our vertex. Now, is this a function? Well, notice as you make your x values along your x-axis, these values are only used once. So where this is a function, this relationship, and you should have this in your notes, is not a function. Now, an easy way, once you have a graph, to check this is this concept here, and it's called the vertical line test. Now, what is that? Well, if we had a very, very thin vertical line, and I'll put one down here too, and we were going to move that line over the face of our graph, would this line intersect this graph in more than one place? Well, when it got here, it would intersect there and there. Here, it would intersect there and there. So the answer is yes. This vertical line would intersect our graph in more than one place. If it does, we say it does not pass the vertical line test. So this would be not a function. Now, as we look at this parabola, y equals x squared, as we pass this line over the face of this graph, does it intersect the graph in more than one place? Well, it's once there, once there, once there, and the answer is it only intersects in one place, not in two places like we see here, only one place. So we say this passes the vertical line test and is a function. And we'll see it right here too. So here our black line is the vertical line test that we're going to move over this graph. Does it intersect this graph, which is the sister of this one, in more than one place at a time? And it's no. So this passes the vertical line test and is a function. Now how about this one? This is just going, instead of low to up, up to down. Does this pass the vertical line test? Yes. So this is a function. Now another kind of line we had was the horizontal line. You might remember the equation was y equals b for this. Is this a function? Does this black line intersect only once? And the answer is yes, this is a function. Now the other kind of equation we dealt with in the previous lesson was the equation x equals a, which was a vertical line. Now as this vertical line intersects this vertical line, it intersects in an infinite number of places. So this does not pass the function test. So this is not a function. So of the graphs we're going to be dealing with that are straight lines, 3 of them are functions. It's only the vertical line with this equation that are not a function. And we just did this one, where you have a sideward parabola. It does not pass the vertical line test. So this is not a function. And hopefully something easy. Let's take a look at this. Here are some examples of different graphs we might have. Does this pass the vertical line test? Yes. And does this one? We just had this. Yes. How about a circle or a ellipse or something? No. Intersects there and there. Now how about this wavy line? Yes. How about this vertical line? Does it pass the vertical line test? No. Okay, something easy, hopefully. And the vertical line test, excellent tool. So, letter A, what do you think? Yes or no? Are they a function? Yes. B? Yes. C? No. D? Yes. E? No. Now, theoretically, we ought to be able to write some of these formulas, by the way. And I think the only one that will jump out at us easily is this one. Here this is going to be y equals 3, and here this is x equals 3. Now later in section 5 of this chapter, we'll be able to write the formula of this, but I don't want to jump too far ahead. Doing the concept check, you may recall that this graph looked like this. Is this a function? Does it pass the vertical line test? Yes. And we said this was the parabola. So this is yes. And this was a straight line. So this is yes. Now, they're asking us to do something specific here in example 6. Now, in example 6, they want us to find the domain and the range of each relation and determine whether the relation is a function. Well, let's do the function part first. Is this a function? For A. Passes the vertical line test, so yes. Now B doesn't pass the vertical line test, so it's not a function. C passes the vertical line test, and D passes the vertical line test. Now, when we say domain, we're looking for the x elements, the range, the y elements. And this is alphabetically, if you ever forget which is which. X, Y, D, R. Okay, so what we do when we're looking for the domain is we project this down to the x-axis. So this is going to start, because of the dot there, at -3 and go to 5. Now the range we project over this way to the y-axis, so it's starting at -2 and it goes up here to 4. So rather easy once you know what you're doing. And for this, the range from a -4 to a 4 for the domain. -4. Yeah, we're using interval notation here. So, and range now goes from 2 to 2. So -2 to 2. Now for this one, for domain, keep in mind that eventually this will go way out there and this will go way out there. I'm exaggerating that, but what do we have then? Well, we have from -infinity to +infinity. Now for the range, it's starting here at 0, and it also will be going up this way, so to +infinity. And for this one, again, it's going to go way out there and way out there, so from -infinity to +infinity, and it'll also go up that way too and down this way. So some good information, and it's in your textbook, and hopefully now it's in your notes. And of course you have access to all of your textbook online. That's where I'm getting it. And there's what they're showing you there. And on the next page, showing you that as well. Okay, practice is similar. Again, for domain, we would project it down. This looks like a -1 to a 2. And then for a -2 to a 9. All right, let's go on to objective 5, using function notation. Now, when we deal with function notation, there's a special way to write it. And that special way is the use of this symbol. F of x is such that, let's say, 2x plus 3. Now you might say, oh, that's very similar to y equals mx plus b. And that's true. And we often say that we can substitute the y for this function notation. Now, a couple of things to keep in mind: that the parentheses here do not indicate multiplication. This is just indicating our x value. So, if we were to say f1, what would that mean? Well, it would mean to take the 1 and replace it where the x is. So this would be 2 times 1, this value for x, plus 3, and we get 2 plus 3 is 5. And we did that in our t-charts in the previous section. Now, we also are giving another definition here. We're saying that the independent variable is actually the x. This is our independent variable, because depending what the x is, that determines what the y would be. Okay? The y is our dependent variable. So as we make a t-chart and we put in various x values, these are our independent variable, because once we put that into the operation here, it gives us our y value, which is the dependent. Another symbolism you sometimes see for function is we say input and output. We're putting in an x value and we're getting out a y value. So this is your independent variable, this is your dependent variable. So very similar to what we've done before. So a strategy when you see things like example 7, where they're giving you this quadratic expression, that is x to the second power, and they're giving you various values here. So for f, that would be a 1 that would go over there. For b, they're giving us a g value, which is a 1 over there. And here this is a -2 for f, and this would be a 0 for our g. And then we just put these as our x value in there, as they're illustrating here, and you get your output, which would go in this column. I strongly recommend you use a t-chart to keep your data organized. And notice that we can also have function with other letters rather than an F, which is the first letter of function. We could have this. It's still a function, but other letters. Others are like H of X and P of X. This would all be function notation. A very, very useful tool, and you see it really is closely related to what we did in section 1. As we look at example 8, Here they're giving us a function in the form of a graph, and they're asking us to determine if one of the letters is given. For instance, in letter A, we're given an x value of 4, and put that in a graph, a t-chart I should say, and a -2. And for the g values, we have a 5 and a 0. So what we're asked to do now is what would be the corresponding pair member if, as we look at this one, we have x is 4, what would be our, in a sense, a y value here? Looking at the graph. So let's look at this one. So we have x is 4. Where is x 4? 1, 2, 3, 4. And we have a point now right there. What is our y value there? Well, it's going to be 2. So this particular point, when x is 4, y is 2. Okay. Now how about if x is a -2? Well, where is -2? Right there. And what is our y value? Our y value is a 1. And that's the solution for this. Now over here they're saying g is 5. So, or our x value for g is 5. So we go to 5. 1, 2, 3, 4, 5. And what is our y value there? We go over there and we see that it's 3. Now, x is 0. Well, x is 0. What is our y value there? It's 0. And that's all they're asking. But again, you need to understand what's going on here. We need to pick up on the title for example 9. The following graph shows the total and outline enrollments in post-secondary institutions as a function of time. So, what are we looking for? Approximate the total enrollment in the fall of 2009. So we'd go fall 2009. Geez, that almost looks like our school there. Could be, yeah? Maybe. Yeah, maybe. I'll tell you, that's interesting. So anyway, you're taking the fall of 2009 and then bringing like a line over to see what your enrollment would be. So it looks like right between the two here, would you say 19 million? All right. So in part B, they're saying the total enrollment in 2002 was this. So you would subtract the enrollment from 2002 to there, and that should give you a number. But again, it's kind of hard to pick out. Okay, well, we said 19 million. So subtracting the 16.6 million from that gives you 2.4 million students. Okay. So for example 10, we're looking at this function right there, and they're asking us to predict total enrollment in the fall of 2010. Well, our data starts in 2000, so that indicates we have the years of 10. So our x value is our time. So we put the 10 where the x is, and then we predict this for 2010. And we'll be doing more of this as we go into the next few sections here. They are dealing with use of graphing calculators. We are not using graphing calculators particularly. There is an online version, by the way. You can go online and ask for a free graphing calculator and use that as a reference. Okay, we'll wind this up and go on to our mini lecture exercises.